Study about equation of continuity in electrodynamics. Equation of continuity actually validates the conservation of charge. We know about the conservation of energy, which says that energy can neither be created nor be destroyed. It can only be converted from one form to another form. For example, suppose we have example of potential energy and kinetic energy. Potential energy is due to the position of a particle. Suppose a body is at rest, then it will stay at rest. Now, if the body starts to move, then the potential energy of that body converts into kinetic energy. And if that body comes to rest again, then the kinetic energy becomes back into potential energy. So this energy keeps on going or converting from one form to another form. Similarly, we have conservation of charge. A charge, say it positive or negative, does not appears or vanishes. A charge is always there in this universe. They just flow from one place to another place. They do not disappear or destruct. Now, we have to have this simple understanding in order to prove how the equation of continuity will validate the conservation of charge. Suppose we have this volume V, and suppose we have these charges inside this volume. Now, if the charges start to move out of this volume, then we can say that the rate of charge is decreasing inside this volume V. Similarly, if suppose we have this volume V and the number of charges are increasing inside this volume, then we can say the charges must be entering inside this volume, which is causing the number of charges to increase inside the volume. This is what the equation of continuity says. Now we know that current is produced because of the flow of charges. And if we have a lot of charges, then we can represent them as rho, or charge density. So if a lot of charges are flowing from one place to another, instead of writing them like Q, we can represent them as rho, which shows the density of all these charges. And this rho contains the value or the total effect of all these charges. Hence, a group of charges or a lot of charges can be represented as charge density. So if there are a lot of charges inside this container, so we can write them as rho. And if the charges are moving outside, or we can say that's a summation of all the charges, can be written as this. Now, if the charges are moving outside this volume, then how do we represent current? We know that I is equal to dq by dt, which is the rate of flow of charge, or the rate of change of charge. Now, if the charges are flowing out of the volume, then the rate of charges inside this volume must be decreasing. So, in that case, current will be represented as minus of rate of change of charge. Similarly, if the charges are flowing in, then the rate of charges inside the volume must be increasing. Hence, in this case, current will be I is equal to dq by dt. Now, another concept we must know in order to derive the equation of continuity, that is current density. Now, if we have a surface S, and if a lot of charges are flowing through this surface, then we know because the charges are flowing, current must be produced. Then we can represent, in this case, current as I is equal to closed integration of J ds over this surface S. What does this J represent? This J actually represents the current density. It is the amount of charge crossing a unit area surface in unit time. Now, if these charges are flowing in open air, we represent them as rho. But if these charges are flowing through a surface, then we can represent the current as J. Now, in order to derive the equation of continuity, we will write two equations or two expressions. One expression we will write for current with respect to volume, and another expression we will write for current with respect to the surface. You may ask which volume or which surface. So let's consider this container, which has volume V and has this surface S. Now suppose these charges, now we'll be careful, for this equation 1 we will only be considering the change or rate for the volume only. So if I say that there is a change in charge or there is change in current, then that will be only with respect to V that we will be considering. Now, what will be the current? If these charges are moving outside, then we can say that the rate of charge is decreasing inside this volume. So we can write it as minus of dq by dt. Now if these all charges can be written as q, Or more specifically, we can write them as rho, as these are crossing or going out of the volume V. So we can say that the rho, that is the charge density, is moving out of this volume. So suppose we have all these charges can be represented as Q charge, a single charge. Then if this charge is going out, then we can represent it as this. That is integration over volume of rho dV. What does this actually mean? This means, and this integration, that is V dV, is used to add all the charges inside this volume V. Hence, this can be written as minus of dq by dt equals d by dt, like this. Now mathematically, this expression can be written as this, because we are specifically focusing on the charge density. Hence, we can take the partial differentiation of the current density and take it inside. Hence, we will get something like this. So this is the expression for current with respect to volume. Or I can say that this expression shows that how is the current with respect to the volume. Now another equation can be written for the same current. Now we know that suppose these charges, these lots of charges Q, are crossing this unit surface. So as they're crossing the unit surface, then this group of charges can be represented here as J. And in order to add all these charges that are crossing this surface, we can put an integration, a surface integral, that will add up all these charges crossing this surface. Hence, the value for current that we get is like this. So now we have two equations. One equation is this, while the other equation is this. So we can equate them, because on the left side we have current in both. Hence, we can write them as like this by equating the right hand sides of the equation. Now we can see that on the left hand side we have volume integral, whereas on the right hand side we have a surface integral. Now with the help of divergence theorem, we will convert the volume integral into, with the help of divergence theorem, we will convert the surface integral into volume integral. The divergence theorem says that suppose we have a surface integral like this, that in order to convert into a volume integral, we will just put a volume integral and take divergence of this expression, and here we will get dV. So this is how the divergence theorem works. Hence we get something like this. So here on the left hand side we have volume integral, here also we get the volume integral. So now we can simply equate them, because the integrals are same. Hence we can remove the integrals. So on the left hand side we've got this, and on the right hand side we've got this. Now this means the current moving out of the surface, because divergence actually tells us if something is going inside or something is coming outside. And since in our container the current, or we can say the charges, are coming outside, so here the divergence is going to be positive. And since this is surface S and this group of charges is represented by J, hence we can say this group of charges are moving outside. This divergence specially shows that the direction of these charges, that is J, is actually outside of this surface. Whereas the expression of the left hand side tells you that inside this volume V, which has a lot of charges which are moving outside, this expression shows that all these group of charges which are represented at S, its rate is decreasing. That is, this rate of the charges inside is decreasing, and decreasing is shown by this negative sign. Hence this shows the rate of decrease of charge within volume with respect to time. Hence this is our equation of continuity, which shows that if we have a container and there are a lot of charges inside, then if the quantity of charges is decreasing inside the volume, which is this expression, it shows that these charges are moving outside of this volume. Only because of that, the charges are decreasing inside. And this right hand side shows that the charges are moving outside. This is our equation of continuity.